Assalamualaikum, students and fellow physics lovers. Today's lesson focuses on computing motional EMF induced in a given length of a conducting rod that slides on a U-shaped conductor. The rod moves with constant velocity vector in a uniform magnetic field vector. How do we determine the motional EMF using the scalar triple product method? To find out, just stick around, watch and learn. The question is, an isolated conducting rod of length 8.00 centimeters is oriented parallel to the x-axis at time equals 0, and A is at x equals 0, y equals 0, z equals 0. In other words, and A is at the origin, and NB is at x equals 8.00 centimeters, and y equals z equals 0. The rod moves with constant velocity vector v equal to quantity 1.50 meter per second, quantity I, plus quantity 2.00 meter per second, quantity j. In a uniform magnetic field vector, capital B equals quantity negative 0.120 Tesla, quantity I, plus quantity 0.150 Tesla, quantity K. Question letter A, find the magnitude of the induced EMF in the rod. Question letter B, which end of the rod, A or B, is at a higher potential? As illustrated in this figure, we have a conducting rod, okay, whose left end is labeled A and the right end is labeled B, right? So this rod is actually sliding on an external U-shaped conductor, and the rod is moving across a uniform magnetic field denoted by capital B, whose direction is towards the positive z-axis. Notice the dot symbol, which represents the direction of the external magnetic field. The dot symbol suggests that the magnetic field is directed towards the reader. So, the velocity of the rod and the external magnetic field are perfectly perpendicular, right? And because of the motion of the rod, okay, cutting the magnetic field across, okay, there is a magnetic force denoted by capital F sub B exerted on the free positive charges within the rod, right? The magnetic force is directed to the right. You can verify this direction of the magnetic force using your right hand rule, okay? So, as more and more free positive charges, okay, are accumulated at the right end of the rod, okay, the left end of the rod, or point A, becomes more negative. Hence, there is also an electric field that is established within the rod, right? So, since point B is more positive than point A, the direction of the electric field is to the left, or from point B to point A, all right? And when there is enough electric field that is established within the rod, okay, we will come to a point when the magnetic force FB is just equal to the magnitude of the electric force FE, right? We are given the length of the rod, capital L, equal to 8.00 centimeters. And the magnetic force FB being equal in magnitude to the electric force Fe, okay, can also be expressed as uh, the product of the magnetic field, capital B, the charge Q, and the velocity of the rod, small v. That is the expression for the magnetic force Fb, while the electric force Fe is expressed in terms of the product of the electric field, capital E, and the charge Q, right? So the charge Q can be canceled, and we come up with the relationship between the electric field, the magnetic field, and the velocity of the rod. That is, the electric field vector, capital E, is just equal to the vector product or cross product of the magnetic field vector, capital B, and the velocity vector, small v, right? And when this velocity vector electric field, capital E, is multiplied by the length of the rod, then we are defining what we call a motional electromotive force, denoted by the Greek letter epsilon. So epsilon is just the dot product of the electric field, capital E, and the length of the rod. All right? So in our figure, this induced motional electromotive force epsilon is directed from point A or end A to end B, as represented here by the blue arrow, right? And for us to be able to quantify this motional EMF or epsilon, we need to apply a concept in unit vectors. We call this the triple scalar product, right? Triple scalar product is just the dot product of one vector. In our problem, this is the length, capital L, of the rod, okay? Uh, and the cross product of the two other vectors, uh, the velocity vector, small v, and the magnetic field vector, capital B. And the complete expression or equation for the motional electromotive force, epsilon, is given here, right? It is equal to quantity, small v, okay, cross multiplied by capital B, and then their product or cross product is dot multiplied to the length, capital L, right? And since the cross product V and capital B is actually the electric field vector, capital E, we can also express the electric or the electromotive force, epsilon, all right, in terms of the product of the electric field, the dot product, I mean, of the electric field and the length, capital L, right? And specifically, the problem is requiring us to determine the x component of the motional electromotive force, or that is labeled here as epsilon sub x. All right? So also included in our illustration is the direction of the conventional current along the external U-shaped conductor, right? Represented by the red arrow. It is from point B, all right, passing through the external part of the conductor and goes into point A. That is the direction of the induced conventional current, right? We can say that the direction is clockwise. Vector product small v cross capital B, or that is equal to vector capital E, can be determined here using the component method. For vector v, or the velocity vector v, that is equal to quantity 1.50 I plus 2.00 j meters per second, its x component is equal to 1.50 meters per second, its y component equals 2.00 meters per second, and its z component is equal to 0. While for the magnetic field vector capital B, expressed as quantity negative 0.120 I plus 0.150 K Tesla, all right, the x, y, and z components are b sub x equals negative 0.120 Tesla, b sub y equals 0, and b sub z equals 0.150 Tesla. To have the formula for the cross product in terms of their components, we write the components of the velocity vector and the magnetic field vector as given here. So the velocity vector, right, is in terms of the components v1, v2, v3 for the x, y, and z components respectively. That is, velocity vector v is equal to v1 I plus v2 j plus v3 k. And for the magnetic field vector capital B, okay, expressed in terms of b1, b2, and b3 for the x, y, and z components respectively. So the magnetic field vector capital B is equal to b1 I plus b2 j plus b3 k. Or substituting the given values for the x component, or v1, we have 1.5 meters per second. For the y component, v2, it is 2.00 meters per second. And for the z component, v3, there is none. Likewise, for the magnetic field, v1, or the x component, is equal to negative 0.120 Tesla. For the y component, capital B sub 2 equals 0. And for the z component, expressed as capital B sub 3, it is equal to 0.15 Tesla. We need to remember that we need to find only the magnitude of the x component of the induced electric field, capital E, or that is small v cross capital B, right? We don't need the y and the z components of this electric field vector. Let's start with by expanding out the cross product V cross capital B. That is, quantity B1 I plus V2J plus V3K cross multiplied by quantity B1 I plus B2J plus B3K. Right? That is, this is the result of expanding the cross product B cross capital B. It is equal to V1 times B1 times the cross product of I and another I plus V1 times B2 multiplied by the cross product of the unit vectors ij plus V1 times B3 multiplied by the cross product of the unit vectors I and k. All right? So this is the first segment when V1 I is multiplied to each of these terms. The second layer is when V2J is multiplied to the magnetic field components, right? Where we get positive V2B1 times the cross product of the unit vectors J and I plus V2, capital B2, okay, and cross multiplied by the product of J and another J plus V2 B3, okay, cross multiplied by the cross product of the unit vectors J and K. And the last layer where V3 K is multiplied to the magnetic field components. That is positive V3B1 multiplied by the cross product of the unit vectors K and I plus V3B2 multiplied by the cross product of the unit vectors K and J plus V sub 3 times B3 cross multiplied by the product of the two K unit vectors, right? And when simplified, this is what we get. All right. So, one of the properties of unit vectors is that when a unit vector, for example, when I is cross multiplied with another I, that automatically is equal to 0. Likewise, J cross multiplied with J is also equal to 0. And unit vector K, when cross multiplied by itself, is also equal to 0. So all these terms that are equal to zeros, okay, are now cancelled. And the cross product of I, unit vectors I and J, right, is in fact equal to positive K. So V sub 1, B2, okay, multiplied by Ij is simplified to B1, B2, K. While the cross product of unit vectors I and K is in fact equal to negative J. That's why V1, V3 multiplied by IK is now reduced to negative V1 times V3J. Likewise, the cross product of J and I, okay, is equal to negative K. So this term V2 B1 multiplied by Ji is reduced to negative V2 B1K. While the cross product of J and K is equal to positive I. So this term V2 B3 cross multiplied by jk, okay, is also reduced to V2 times V3I. All right, the cross product of unit vectors k and I is equal to positive j. So that term V3B1 ki reduces to positive V3B1j. And last but not the least, the cross product of unit vectors k and j is actually equal to negative I. So that term is reduced to negative V3B2I. When simplified, the cross product of the velocity and the magnetic field vectors can now be expressed as quantity V2 times V3 minus V3 times V2 quantity I minus quantity V1 times V3 minus V3 times V1 quantity J and plus quantity V1 times V2 minus V2 times V1 quantity K. So this is now our working formula. And with our given magnitudes of the velocity vector components V1, V2, and V3, as well as the magnitudes of the magnetic field vector components B1, B2, and B3, all we need to do is plug in these values into this equation. So this is what we get. V cross capital B equals quantity 2.00 times 0.15. We do away with the given units for simplicity. So minus 0 times 0, quantity I, minus quantity 1.5 times 0.15, quantity J, minus 0 times negative 0.120, right? Plus 1.5 times 0 minus 2.00 times negative 0.120 quantity K. So all the terms that equate to 0 are all cancelled. Using determinants, we take only the x component of the electric field, that is E sub x, or the vector product of V and capital B is now equal to quantity V2 times V3 minus V3 times B2 quantity I, where V3 and B2 is equal to 0. So that means the x component of the electric field is equal to 2.00 meters per second times 0.150 Tesla, or the x component of the electric field, all right, has a magnitude equal to 0.300 Tesla meters per second in three significant figures. Finally, we now have the answer to question letter A. The dot product of the x component of the electric field and the length capital L of the rod gives us the magnitude of the x component of the induced EMF epsilon, right, which is equal to 0.300 Tesla meter per second multiplied by 0.0800 meters. That is, the x component of epsilon, or the induced motional EMF, okay, on the rod is equal to 0.0240 volts, also in three significant figures. Right? Um, so this computed value of the motional electromotive force, okay, or epsilon, right, is just the same as the potential difference, right, capital V sub BA, where point B is considered at a higher potential compared to point A, right? And that is equal to the cross product of the velocity vector V and the magnetic field vector capital B. The cross product is that multiplied by the length of the rod. So earlier, we called this the scalar triple product, right? And in question letter B, right, in the U-shaped conductor, you may refer back to our illustration. The electric field capital E actually pushes the positive charges to move from point B or end B of the rod to point A or end A of the rod. Hence, end B is considered at a higher potential compared to end A. Right? So on this note, may I say mabuhay till the next episode. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.